you all for coming today. It's so nice to see so many friendly faces. So we're lucky enough to be hearing from our co-director, Nick Eyre, this morning. Nick is also the director for CREDS, the Centre for Research into Energy Demand Solutions. So today Nick's going to be presenting on rethinking the zero carbon energy transition. If you've been to one of these sessions before, you know that they're very open, so feel free to chime in and ask questions at any time. And if you're online, do the same, or feel free to just put things in the chat and I'll be monitoring it. And yeah, I think we'll just launch straight in. Thanks, Nick.
Thanks, Eleanor. So this work is, as you say, branded as an output of CREDS, and look, much of it has been done under CREDS, but actually the initial thinking was done as part of Integrate at the time that I was thinking about where heat fits into the energy transition and thinking about, therefore, how much energy is needed to supply heat in the UK. Once I thought about the UK, I thought, yeah, let's think about the world instead, because it's a bit more fun. That's what I've done, and the slides don't seem to go down.
There we go, just this. Yeah.
Okay.
Yeah.
Right. So what I want to persuade you, and I think for this audience, I don't really need to persuade you for the first of these, that getting to zero carbon requires major changes in whole energy systems. If you don't believe that, then I'm not quite sure what you're doing here. I then want to persuade you that this is to do with thermodynamics, which is a bit more of a challenge, I think, and finally to argue that the transition will significantly improve energy efficiency, which is sort of standing on its head of a very common argument that we need energy efficiency to enable the energy transition. What I'm trying to argue is almost the other way around, that the energy transition will enable energy efficiency. Bear with me. So it's published, this is published recently in Energy Efficiency, and yes, it was mainly done with CREDS money. Just so be clear, when I talk about an energy system, I'm talking about the system that takes primary energy sources and delivers energy services. So it includes everything that you would expect right the way through the production chain. That's not always the case, of course. The common representation of the energy system is this one, the Sankey diagram. Known and loved since 1898. It was interesting doing this research to go and look where Sankey diagrams came from. There's a man called Sankey, not surprisingly, and he published it in 1898. So this is for Europe, and I don't need to explain to this audience what it's about. But it does seem to me there are some problems with Sankey diagrams. The problems are hidden a bit on my screen behind the pictures of you all. But basically, I think there are three problems with this version.
Click the little minimize button and they'll go away.
Am I allowed to do that?
I think they're still there.
Yeah, they're still there. Yeah.
Right. Okay. It ignores what we use energy for, that the energy services sort of get left off a traditional Sankey diagram, which is a bit annoying for those of us who work on end use. It treats all types of energy as being of equivalent value, and I'll come back to that. Those of you who know about exergy will already know that. And the third is it's a bit complicated for thinking conceptually, so it'd be nice to simplify it if we can. So taking those three in and what I want to do is then produce something that looks a bit like a Sankey diagram but addresses these problems, because I think that enables us to think more clearly about it. So basically, I'm going to want to extend the diagram to the right to include energy services, thermal comfort, mobility, etc. And then I want to think about the value of different sorts of energy, which is to do with thermodynamics. I suspect I've got a mixed audience in terms of thermodynamics, from people who think it's all totally obvious to those of you who might be slightly worried by listening to a talk about thermodynamics. Don't worry, that group, you don't need to know a lot. Basically, there's an interesting quote from Einstein there, which I thought I'd throw in because it's always good to have a quote from Einstein in a talk. But thermodynamics does show that not all energy is of equal value. That's sort of that's the bottom line for this talk. And the thermodynamics that you need to know basically is the first and second law. First law says that heat and work are both forms of energy and can be converted into each other, and that when you do that, energy is conserved. You can't lose or gain energy. You can only convert it to different forms. The second law, which is more interesting and relevant to this piece of work, is that there are limits on conversion efficiencies. The diagram on the right there is one that anybody who's done physics or engineering would recognise. Heat flowing from a hot source into a heat engine with waste heat going into a cold source and work coming out, and you can reverse that if you want. You put work in and drive heat from the cold source to the hot source, and that's basically what we do in a lot of conversion processes. And so QH plus is equal to QC plus W is the first law, and the second law is about how much W you can get out given different temperatures. That is all the thermodynamics you need. It's actually pretty much all the thermodynamics I remember from 40 years ago, but that's what you need for here. So we need to think about heat and work as having different values to think about this. My third complaint about the Sankey diagram was that it was too complicated. So I'm just sort of going to simplify things quite a bit. So what I've done, this is my revised Sankey diagram, if you like. So there's nothing quantitative on here, although the thickness of the arrows has no relevance anymore. This is just about the sorts of flows you can get in energy systems. And what I've done, the main change is, rather than thinking about coal and oil and gas, just think about heat and work, basically. Because it seems to me there are two sorts of energy sources. There's those that naturally produce heat, the fossil fuels, also nuclear and geothermal. We don't really know any other way to use them but to produce heat. And then there's the ones that more naturally produce work, hydropower, wind. Solar can, of course, produce heat, but most of the solar that we're now talking about is solar PV, so it goes straight from light to work, actually. And then at the other end of the diagram, there's also a sort of natural split between heat and work. There's energy services that are about heating things up, space heating, washing, cooking, drying, making steam, melting stuff. And then there's energy services that are about work, stationary power, transportation, data processing, electrochemistry. I put lighting in there. Lighting is a really annoying one to think about because it's sort of changed from being about heating to being directly produced from electricity without heat. So the paper goes into all the sort of difficulties and complaints that you might have about this simplification. I recognise it is a simplification. But basically, then I've simplified the middle. There's some ways that you can use the heat things to provide heat. You just go to solids, liquids, and gases as final fuels and put them in boilers or dryers or furnaces. There's obviously the work tends to come out as electricity, which you can put into motors and appliances. But then the annoying and complicated bits of Sankey diagrams are that you can turn electricity into heat, or you can turn solids and liquids directly into work using engines at the point of use, rather than engines to produce electricity. So it gets a bit messy in the middle. That's still too messy for me. So what I wanted to, my starting point was thinking, well, all this stuff about thermodynamics and these conversion processes is what happened in the Industrial Revolution. What did this look like before the Industrial Revolution? And the answer is, well, we didn't have an energy system anybody would have recognized, or rather we had two energy systems. We had a system that produced heat from actually mainly wood in those days, burning wood, some fossil fuels. And that produced the heat services. And then we had other things to produce work, stationary power and transportation. And actually, it was mainly either human beings or other animals that did that sort of stuff. There was a bit of hydropower and wind to do things like milling of grain in specialised locations. But mainly, if you wanted to do some work, you did some work. That's why it was called work. You actually got off your backside and did something, or pushed something, or you got an animal, a tame animal, to do it for you. So it was only really the Industrial Revolution that muddied this system up. John, yeah.
Sorry.
No, it's the Malcolm McCulloch challenge. You've got to stop me to get into the end.
I think just thinking pre-industrial to then, because that's what you're on.
Yeah.
Shouldn't you regard the whole agriculture process as part of a total energy system? Because increasingly that's now part of the carbon.
Well, human labour and animals are powered by agricultural produce, yes. That's where the work comes from.
And the animals have to be powered by the crops.
Yeah, exactly. So, yeah.
So it's in there.
So,
you haven't broken down.
I mean, human beings can work at about what, 100 watts, and we now use something like 3 kilowatts per person in this country. So we use about 30 persons worth of energy. I think.
Just I used to have a colleague who complained that humans were very inefficient converters of food into energy.
Probably, yes, because actually they're not really designed just to do that. That's the problem, isn't it? So.
And therefore he felt he ought to take the bus to work rather than cycling. Sorry, I wouldn't interrupt.
I still but yeah, so cycles are now very advanced products, aren't they? So I mean, you've got some real cycling experts in this room. Yeah, very high efficiency. Yeah, high on the box.
My point really, I suppose, is you've got land use as part of an energy system.
Yeah, you're right, John. And of course, what I'm trying to do is simplify stuff rather than make it complicated. So that's my excuse.
In which case, I apologise.
Right. So what happened in the Industrial Revolution was pretty profound, really. Now, I'm calling these stereotypical. So this stereotype of the Industrial Revolution neglects things like hydropower. But actually, in many countries, particularly like the UK, we stopped doing all this stuff here, animals and human beings doing things, and we went pretty much a heat supply dominated energy system. And if you wanted to work, you either converted it to electricity by the end of the 19th century when we invented that, to do it that way, or you burnt it at the point of use in an engine, which was the original way of producing work. So engines were to replace human and animal labour power. And so we ended up with a system that is heat dominated, heat supply dominated, but for a mixed set of energy services. Robin?
Arguably, you talked about biomass before, that had its problems because it cleared a whole area of forest and it generated faster now. So even the quote renewable approach using biomass was not really.
Right, I always refuse to talk about bioenergy because it's just too complicated. But certainly, I mean, what as I said, in the pre-industrial systems, heat was dominated by biomass. Here it wasn't, because there's not enough biomass to produce the sort of levels of energy that we want globally. Right. So that's my simplification there. And we do have a heat-dominated system. That's what current global energy use looks like. I've split it into the 3 main end users. And within those, some various categories, and basically the blue is direct use of fuels, and the red is electricity. So heat's largely provided by direct combustion of fossil fuels. There's a bit from electricity, but not much. Work in buildings and industry is largely provided by electricity. In transport, it's largely produced by liquid fuels still, because of the annoying habit of transport vehicles of moving around, makes that harder to supply with electricity. And that electricity is, of course, largely from fossil fuels as well, still in most places. But electricity only provides 26% of final energy. So that's really the bulk of the decarbonisation challenge, as now I think, isn't it? Is decarbonising the rest of it. We now have to do electricity. yeah, big yellow banner says it all really. We can't go on using fossil fuels at the point of use, although that is the dominant use of energy in the world today. We have to change that within the next 30 years. That obviously involves changing the fuels, but the critical point that people like me always insist on making, it involves changing fuels at the point of use as well. It's not just an energy industry problem, it's a whole society problem. So we often think of the energy transition now as, and in this heat work categorisation, I think it falls into 4 stages. Firstly is the decarbonisation of electricity. Mainly, I will argue that will be by work producing renewable energy sources, wind and solar. We then need to convert the end users of work that currently use fossil fuels, principally in transport, to use work, and that's what electric vehicles are. We then need to start worrying about decarbonising heat, and we can use electricity for many of those purposes, particularly where it's relatively low temperature heating, and that's what heat pumps are. And then, of course, we're left with the difficult stuff, which is hard to electrify, you know, marine aviation, industrial process stuff, where we need some other zero carbon final fuel. That's going to be hydrogen or maybe ammonia or other sort of hydrogen rich things. And if we want to really get out of fossil fuels, we have to produce that from electricity, which of course we know how to do, although it's currently rather expensive. So that's the sort of energy transition. When we've done that, if we can succeed in doing that, we end up with an energy system in 2050 where the end users are broadly not the same that we have now. We still need probably the same set of energy services. But whereas the post-industrial system, industrial revolution system was quite dominated by heat, it will now be dominated by work, right? So it's a massive change, right? So everything that was up here and went down there has disappeared, and everything that's up there has gone down here now in this diagram. To me, that's like such a massive change that that people often focus on what's going on here. I think that's the dominant way to think about energy is we need these things to produce those to replace these things. But if you've got the same set of energy services, that means the whole of the intermediate system, all that muddled up bit in the middle of the Sankey diagram needs to change as well. Yeah.
We have a question from David. David, do you want to chime in?
Yeah, Nick, I noticed that you've done away with the low carbon heat sources of nuclear and geothermal to try and do 100% renewable.
Yeah.
So I'm interested on your comment that so there's been an analysis of the German system, because the Germans are trying to do this, that they need 28 terawatts of storage to enable them to cover even the current low generation periods for their renewable sources, or they need to just buy all their nuclear off the French.
Yeah, you're right, David. It's probably another talk, and I think we should try and get Chris to give it when he's finished his report for the Royal Society about how much storage we need. Work just published by my colleagues at UCL about the UK says that the number you quoted is about right. It's tens of terawatt hours of storage that we will need in the UK, and that means it's not, it's not mainly electrochemical. It's either chemical or
yeah. That doesn't also.
But I don't think shed loads of nuclear power changes that a huge amount, actually. I mean, it does a bit, but you've still got a very, very peaky heat system to supply, which you probably would need quite a lot of storage to address. So yeah, I mean, it's a good point, David, and yes, again, it's my massive simplification here by saying, okay, wind and solar are likely to be very important, so I'll look at a system that's entirely wind and solar just to see what it would look like. It's not meant to be a a representation of the way the world will be. It's a sort of exaggerated version.
Yeah, especially with future climate scenarios and global stilling, for example.
Sorry, say that again?
So the prediction is at a 2-degree global mean temperature increase, we'll see something like some fairly significant percentage of decrease in global wind speed, which obviously is not a great one if you're depending on wind for your power source.
I thought that was still, I mean, I don't know. I thought that was still disputed, the effect of.
There's a couple of more recent papers that are quite good analyses on that, particularly around
Right.
our area.
I mean, we would think that the capital costs of wind technology will go on going down, so again, these things are going to be in competition with each other. And globally, solar is probably the most important resource, and that's huge anyway.
So Nick, I was just wondering if you've got away with it by saying fuels. You still mentioned the word fuels, and one of the characteristics of a fuel is you can store it. So you kind of bundle storage into your top of the diagram, but you haven't explicitly brought it out. Yeah,
it's something that I think it is probably an interesting area for many people to think about. The hydrogen, there seem to be two bits of work going on, large bits of work going on hydrogen. One is about the use of hydrogen as a vector, and the other is about hydrogen as a storage system. But there should be synergies between these. It should be the same hydrogen. And I'm not sure that anybody's really adequately thought that through yet. Okay, so that's my point about the changing system we're looking at. If you look at what the implications are for energy efficiency of those 4 stages, the switch from thermal power generation to wind and solar doesn't impact directly on final energy use efficiency, but it obviously increases primary energy efficiency because you all those power station losses of displaced from the system. The next stages, the replacement of work from using electric motors rather than heat engines, is a huge increase in energy efficiency. It's an electric vehicle compared to an internal combustion engine, factor 3 probably. The third stage, getting heat from electricity rather than from fossil fuels, similar, factor of 3 improvement, usually that sort of amount. The last stage, stuff that we might need hydrogen or something else for, a bit more complicated. Clearly, the production of hydrogen is not 100% efficient, can't be. So that reduces the efficiency of fuel production. But actually, you can use hydrogen more efficiently than fossil fuels, notably in fuel cells. So it's a bit complicated. But you can see from my colour coding that it seems likely that the overall outcome will be an improvement in energy efficiency. So as a generalisation, pre-industrial energy systems, heat and work were separate. We then had the Industrial Revolution, heat became the main energy sources, converted into work where we need it. And we're now going through another industrial revolution, I think, just moving into it, where work will become the dominant source of energy and that'll be converted into heat where we need it. Right, it's a very simple thesis. It's so simple that when I tell people, they say, yeah, that's obvious. I think it is obvious. No one had ever actually published that before in that form that I can see, which is very odd, very strange that no one has really represented it in that way, but they aren't. You know all that, so I'll move on. So I said, I think this will improve energy efficiency globally. How much was the question? And so that's what the bulk of the paper that's published is about. So the assumptions I made were the ones I've set out, that 100% of energy comes from work producing zero carbon energy sources, wind, solar, hydro. Energy use is electrified where you can, otherwise it's energy supplied by electrolytic hydrogen. Demand for energy services is constant, and the only energy efficiency changes are due to fuel switching. None of that, let me emphasize, I don't expect any of those to be true. right? That's what, this is not a scenario, it is a thought experiment, right? But it does seem to me that it's useful to know what the effect of the heat to work switch is on energy efficiency, without muddling in all the other things that you do if you produce an internally self-consistent, plausible scenario. Then the methods were, well, pretty dull, really, to be honest. Divide global energy use into categories of energy use designed to produce different energy services, then go through each one of those in turn and determine the share of demand that can be electrified and assume the rest will be supplied by hydrogen. And then for each end-use fuel combination, estimate the current final efficiencies in the global system, use the literature to project what the final conversion efficiencies might be in the new system, subtract one from the other, that's the change in demand, and then aggregate back across all categories. As I say, not a very exciting methodology, but seems like the only way to do it. And this is what you end up with in these the categories, and the big categories: industry, buildings, and transport. And the two obvious takeaways are that the global energy system becomes hugely electrified. The share of electricity goes up from 26% to 77% because you've tried to electrify as much as you can. And the final energy demand goes down quite a lot, particularly in buildings and transport, and overall final energy demand is reduced by 40% to supply the same set of energy services, which of course you would expect to change over the period in which you actually do this. If you look at a more detailed level using the breakdown that I showed you earlier, so the top part of the diagram is the current world energy supply that I showed you earlier, and the bottom is what you end up after this thought experiment. And I've kept electricity in red, and I've put hydrogen in a sort of pale blue colour because that's the sort of analogue of fossil fuels in the current system. So energy demand falls in all those categories except the ones that are currently electrified, where I'm assuming there's no changes in efficiency. But in the real world, clearly there will be. Demand falls most in light vehicles and in the building sector, the parts of the building sector that use heat, large space heating and hot water. That's driven essentially by electric vehicles and heat pumps. That's most of the effect. There's quite a big effect in cooking, and that's because I'm heroically here assuming that all cooking is electrified. That doesn't seem very heroic if you think about the UK. If you think about the world, that is a heroic assumption, right? But that's sort of what we need to do in the long term. We don't want women and children going out and gathering firewood. We want to try and get these into clean sources. But that's why there's such a profound effect in cooking. Usage of hydrogen it gets a bit concentrated then in the hard to electrify industrial processes, in HGVs, aviation and marine, and I think that's sort of consistent with the way most people, I mean, this came out of looking at the literature, that's why most people think we won't be able to electrify. It's quite a spectacular change, isn't it? I mean, if you did, I know when you do that for the UK, you get this one, building heating and cars sort of dominate everything else, and they both come right down in this. So you're left with, the difficult to electrify industrial processes, and then lighting, cooling appliances, etc., as your biggest energy users.
Yeah, Nick, we've got a question from David.
Yeah, so in terms of your drop in total energy use for light vehicles,
yeah,
you mentioned that this is because of efficiency increases, but in some ways that obviously doesn't include any of the losses during transmission or anything else. So that's sort of plug to car efficiency, I suppose you're talking there.
Yeah, this is, yes, David, should have clarified this. This is final energy use.
Yeah.
In the paper, I do an assessment of how that might affect primary energy use. And I actually think it probably won't be that different, because in terms of losses in the overall system, we're getting more losses largely from hydrogen production and moving much more electricity around. Those are the two increases. But then you're getting a big reduction in losses, basically mainly in power stations, actually, and power stations and refineries. So it looks like they broadly even out. Right?
But your total amount of transmission network is increasing because of development globally, so your losses will increase. But my main point was more actually, won't the increase in efficiencies that you say for cars and things like this effectively be counteracted by the increase in actual usage because of global development? People around the world will want cars, so it'll basically, the efficiency will go up, but their total number of vehicles is likely to explode.
Right. Next slide, David. Okay.
Yeah.
More questioning?
All right. Yeah. So.
Do you want to keep going? And then
No, I'll take the question now.
Katie, do you want to chime in?
Sorry, I'm in a cafe, sorry, that's why I just wrote it rather than speaking. But I think Nick answered it actually, which it was just a question about the hydrogen losses, and that was answered by the primary versus kind of end use. So thanks, Nick.
Nick, just before you move on, may I ask a question? Will you be talking about energy related products legislation or directives, because the two big bits are still sticking out like sore thumbs on the bottom?
No, I won't. But because you can't talk about everything, right? But yes, yeah. If we electrify most things, then those small, often small, but not always that small changes in efficiency that we can get in other ways become increasingly important. Yeah. It is a point that I think is worth reinforcing, that we don't just want to move to electric vehicles and heat pumps, we want to move to efficient electric vehicles and efficient heat pumps, and that will make a lot of difference. Whether it's factor 3 or factor 4 will be a big factor, and I think that gets missed in a lot of the current debate. So what about the real world that David's question was about, rather than this bizarre thought experiment? So conversion efficiencies are clearly not the only variable. The other things that we might expect to change are other types of energy efficiency, particularly in buildings, improved building fabric was represented nowhere in there, and modal switching in transport, which unlike most people who work on transport, I think of as energy efficient too, because public transport and cycling and walking are more efficient than private vehicles. We will see some of the social changes that might help overall system efficiency. I'm thinking of things like less use of energy intensive materials because of the circular economy, but also the whole gamut of things that digitalization might produce from better control technologies through towards vaguely entitled the sharing economy. I mean, that can make things worse as well as better, of course, depending how you do it. But David's question is absolutely spot on. Rising incomes, particularly in the poorer countries in the world, is very likely to drive rising demand for services, particularly for basic energy services, and that is not a bad thing, of course. That's a good thing. And maybe we also need to think about the luxury goods and services, which are that tend to be the growth areas in the developed world, particularly aviation. So what does it mean for the overall system if you do a more rounded scenario? Well, that's the sort of work that Arnulf Grubler and Charlie Wilson and others did and published in 2018, making ambitious but not ridiculous assumptions about how we can reduce energy demand in sensible ways. And that they reckon that we can halve energy demand in the global north and even reduce energy demand a bit in the global south. The global south now includes countries like China, which use as much energy per capita as we do in the UK. So it's not perhaps as unreasonable assumption as it might have been a few years ago. But obviously that question of how much can we affect global energy demand is going to be critically influenced by this question about how rising incomes in the new energy economy affect overall energy demand, and there's not a simple answer to that. I just thought I'd show you a graph from some work that Chris published a couple of weeks ago, by John Barrett and others, which attempted to which has developed some low energy scenarios for the UK. And the 4 lines on there, the orange is a sort of business as usual, do nothing. And then 3 net zero compliant scenarios with different levels of ambition for energy demand reduction. And the quick takeaway is that energy demand falls 30%, 40%, or 50%, depending how ambitious you are about some of the assumptions about reducing energy demand. The 30% is pretty much driven by the work that I've described here, by conversion efficiency improvement. So, you know, without trying to do much on changing diets and reducing aviation and improving building efficiency and materials efficiency, all of the things you can do, just a sort of, heat pumps, electric vehicles probably takes you down that red line. So anybody who tells you that we're going to increase energy demand in the UK as we decarbonise, it's certainly nonsense. There's no plausible way of doing that. But 50% looks possible. And at 50%, I think we're using about 1.5 kilowatts per person. So that's only 15 times what a human being themselves can generate, which is compared to 30 now, and I think it's 50 in the US. That's the number that Stephen Chu always quoted.
Is that average or peak?
That's average. Yeah.
But 100 watts per person is probably close to peak. And if I think back to my turbo trainer days, that's probably like you could maintain 300 watts for a few minutes. And that's like a toast.
I don't know, I'm sure I couldn't.
Yeah, well, but you're certainly not kicking out 100 watts when you're asleep. And,
okay.
Yeah.
No, 100 watts is almost a standby metabolism.
Sorry?
100 watts is almost a standby metabolism.
Oh, is it? Okay.
Yours, Phil, maybe, yeah. But
But arguably, that's not useful work being done, is it?
Well, keeping yourself warm is quite useful. And goes in the room, it can be recycled.
it's
Cycling hard's probably about 250, isn't it? Sort of peak effort, 250, 300.
yeah.
500 for a top class athlete.
Yeah. Anyway, but 1.5 is average, not
Yeah,
peak.
right, okay, that's what I wanted.
And of course, the peak depends on. I mean, it's seasonally very in the UK, but most of the world isn't like the UK. Most of the world is cooling dominated, so very different properties. So we think it's possible with social change to reduce demand by 50%, but without significant social change by 30%. Some of my credits colleagues don't like me saying the second bit, but I think it's important to give a balanced picture. So those are my conclusions. I've actually got to the end, haven't I? In a post-carbon system, energy system, the main sources of energy will produce work and not heat, and that is a massive change. So final energy will be dominated by electricity, and electrolytic hydrogen is the way I've looked at it. And that requires not just major changes in the upstream energy system, but in how we use energy, and that's the fundamental point, I think. The key technologies then, things like electric vehicles, heat pumps, fuel cells for hydrogen, allow much more efficient use of energy, and that's about 40% effect, which is huge and not generally recognised, I think, in the way that people talk about the energy transition. What it means is that the shift to energy and improved energy efficiency are not independent things. They are going to be very strongly linked and synergistic. And again, that's harder to model and understand because people like to be able to separate things out in terms of the carrier identity and those sorts of ways of thinking about it. It doesn't entirely work. Well, almost all everything I've talked about ignores people. Apologies about that because I shouldn't do that, and I don't normally do that, as most of you know. But actually, where people fit into this bigger systemic change and how they interact with these technologies is obviously going to be critical. And yeah, further research needed. Yeah, as always. That's it. Thank you. Oh.
I've done a fun little bottom-up estimation of how much energy you need for the energy service that we currently enjoy. I came to about 180 watts from first principles information. So the rest is sort of wasted. We still have
so the analysis that Cullen and Allwood did for the global energy system and what the thermodynamic limit was about a factor of 6 different from now. So that would be not too far off. Yeah, I think 180 is quite optimistic.
Oh yeah, and there's some hilarious assumptions.
Yeah.
What I was wondering is, basically delighted that we have energy services as your model. Does that change how we would view things like loads of light being out there and we're lighting with electricity?
Yeah, it's another sort of footnote to the whole paper, which it basically says the way we measure energy is very bad. What we measure is energy that people buy and sell. Yes, that's what energy statistics include. So they don't include the light that comes in through windows or the heat that comes in that way, which is about, I think, 25% of domestic heating in the UK is passive solar again, right? Doesn't count the energy used in cycling, or that it doesn't, because to take John's point, it doesn't include that the agriculture system has an energy supply system, though it clearly is. It's just that the history of energy statistics, they are a commercial set of statistics, and they've been slightly modified in the UK, so they've now got wood fuel in there as an estimate, but it's an estimate. How much wood do people go out and collect to burn in open fires or wood stoves? The short answer is nobody knows, whereas we've got a pretty good handle on the energy that's bought and sold. So yeah, it's a big problem. It's that we don't actually represent it. Well, it's because it's economics and not physics that we're representing.
But like by analogy, is it sort of like how we measure the energy system is as flawed as measuring the economic system of GDP? It seems like to trigger very similar things, like you can look after someone else's children and that will count as GDP, but if you look after your own children, it won't. Yeah,
exactly.
Yeah. And so with heat pumps, you're also the latent heat that is there, it's also not included in the Sankey diagram, right? Because it's a bit like the agricultural, it's just somewhere on the left. Is that right?
Yeah, no, ambient heat is an interesting question, isn't it? Because it does go back out again. Right. It's but yeah, yes, you're right. I mean, the other way to represent all of this is to say, well, it's not really an efficiency improvement at all. And if you look at exergy as opposed to energy, then there is an effect actually, but it's much smaller. So some of the criticisms I've had of the paper are, well, you should do it all in terms of exergy, and then you don't you get the same answer but with a different metric. To which my answer is, well, yeah, you go and persuade the governments of the world to produce all their energy statistics in terms of exergy, and then I'll accept it. There's no chance, because it's hard enough to get people to understand energy without trying to get them to understand exergy. Well, Sam.
So I'm also left with a slightly kind of so what question, because you're talking on the left-hand side of your Sankey diagram about transformation. And as we know, like cars are 10% efficient. Like efficiency in itself is not necessarily valuable as long as the energy service that you're getting. Of course, it's all the externalities associated with that waste and fossil fuels. It is a problem, but essentially, you know, so in your post carbon system, we're using less energy, but the sources of it are much more difficult to come by, arguably, than digging up coal. But from where we stand now, it is anyway. And so what?
Well, you need a much smaller energy system. Is the answer. You need, if you do the crudest thing you can do in thinking about transition and think, well, we have the current energy system, and then all we do is sort of take out the carbon by changing the upstream stuff, but we'll still need as much energy. What I'm saying is that's wrong, right? That cannot work in that way, right? It will be probably about 40% smaller. Does that matter? Well, depends who you are, doesn't it? I think it matters quite a lot in terms of because the speed at which we can do the transition is affected by how much energy we need to replace, how much fossil fuel energy we need to replace, and it's not the amount that you first think of. Is the takeaway.
Nick,
Yeah.
So some transitions though, I heard somebody talking about cycling earlier, and this is quite an interesting one.
Oh yeah, we got another keen cyclist on.
Yeah, well, so one of the points that I make to my students actually is that when I cycle, yes, I don't use car energy by driving in, but I increase energy utilization elsewhere to compensate, because I need to eat far more food because I burn a lot of calories. And obviously I need to do a lot more washing because I don't want to smell. So from that point of view, it's a very simplistic transition, that one, but there are, we make one transition and it's never as simple, as the model suggests. And so how we ensure that we fully capture all of the knock-on implications is quite an interesting problem. Yeah. You mentioned third world cooking, for example. Well, yes, at the point of use, they will end up utilizing a much cleaner source, but those items will have needed to have been produced, and therefore there are other parts to that transition, not just the bit that you see, I suppose I'd say.
Yeah, agree. It says at the bottom, David, systemic change will also involve people. Further research needed.
But it's about cataloguing those additional components.
Completely agree. Yeah, completely agree. Phil and then John.
Maybe a response again. I mean, often it's not that simple. Cycling actually it is. For you to Christopher Pratt for the numbers on that. I think cycling really is pretty straightforward.
But not the washing that David feels he needs to do.
Yeah, that's.
No one's sitting there. No one's sitting near Phil at the moment.
Sorry?
No one's sitting near Phil at the moment. This is the washing.
I cycled down from Henry.
I'm getting a faint whiff of lavender, David.
Well, hey.
But my question was, when you said there's different values to different energies, and let's talk of energy. Made me think, is there another game potentially in these numbers where we sort of cascade different values of energy? So your laptop at the moment produces the services supposed to provide light and information computing, but it also generates heat, which now actually then becomes heating the room.
Yeah.
Value. Is there more we can pull out of
that? Probably, though it's complicated, of course, because heat from a laptop here now is useful heat. But heat from a laptop here in June would be the opposite of that. So, it's.
Well, if you look at an EPC and how crude that is, an awful lot of effort went into the heat output from a conventional light bulb being displaced. Yes. And like in the kitchen, there's always a heat source that's deliberately trying to heat it anyway. So there's a degree of attention to detail that seems completely out of scale for the context of what you're describing here.
What I'm probably more thinking is if you have an industrial process that uses an awful lot of heat in order to get a network, then you don't have two separate independent needs for energy. But you've got sort of, you know, an exogenous sort of cascade.
One of the outcomes of the system I've talked about is there is less waste heat knocking about than there used to be. That's sort of the point. If we're going to make heat out of work, then the reason it's more efficient is there isn't all that waste heat. Right? So I am quite worried by scenarios where people assume that they will have heat networks that run off waste heat, because you need to tell me where the waste heat is coming from.
Just following on from that point, of course, there's a lot of discussion about how you cluster different industries together. You know, the high heat supplying the medium heat, supplying the low heat, so that by the time you get to the third business, there, as you say, Nick, there is no waste heat.
Yeah.
It's
and we shouldn't think that's not been done. That's been done through pinch analysis since the 70s, 80s. I mean, you know, people have understand how to design industrial plant in that way, which is probably.
But it's more about actually bringing different businesses that wouldn't have been co-located together previously to ensure that they're.
It's true, but I mean, if you look at the waste heat sources, and Jeff Hammond at Bath did quite a bit of work on this, they're dominated by a few sites, basically steelworks and refineries and a few other things. Yeah. John.
Yeah. I have said, I think it's a very neat concept you've introduced, which in a sense summarizes an awful lot of things that are really about the way we've been thinking collectively. One thing I've got to share very quickly, it's the best summary I've ever heard of the laws of thermodynamics. And, first law, you can't win. Second law, you can't even break even. But
there's a very nice Flanders and Swan song as well about laws of thermodynamics.
The main point I wanted to ask there was about you were talking about we don't know how the demand for energy is going to increase in the future. And I think I think somebody once referred to it as Newbery's law, but I can never find any reference.
The Newbery-Bashmakov law.
Is that the one? Well, the essence of it is that the proportion of income spent on energy remains constant across different societies.
Yes.
And I've heard there's an interesting bit. It's different actually, but it's the commuting time, home to work. The amount of time spent commuting has remained remarkably constant over centuries. Even though walking has been replaced by.
So, and that would be my question. I don't know the answer to this. Over what time period? Because it seems to me that almost the definition of a transition is that some things are fundamentally different after it than before it. So my question is, the so-called Newbery-Bashmakov constant is about energy expenditure. And I'm not sure that energy expenditure is all that different.
Well, no, well that maybe, but of course you then get into that relates back to the sort of the G-bond thing or the rebound.
Right.
By improving the efficiency of something, you subsequently increase the demand.
Right. So that is a fundamental point that comes out of this, which is that Jevons law is about economics. It's about it's either the total cost of supply or the operational cost, depending which bit of the rebound effect you're looking at. But if you currently replace a boiler with a heat pump, you're not going to get a rebound effect because you're going to pay more than you did before. Sure. So you get whatever the word is, an unrebound effect.
But there will be areas where your efficiency has genuinely improved. It will be cheaper, at least in terms.
Yeah, and EVs are the obvious case, but that's to a large extent an artifact of tax policy. Right. It's only because we don't tax electricity for car use, and we do have a huge tax on petrol, which is that's a good thing. I'm not saying it's a bad thing, but I don't think the actual operating cost of an electric vehicle is that different from in real terms, is that different from an ICE? And certainly the engine costs more than the batteries.
But the issue is really that the cheaper energy becomes to use, the more uses people will find.
Right.
Some of them.
And that is my massive complaint about rebound, about the way rebound effect is used. It is used as a stick with which to beat energy efficiency. And I will take it seriously the day I hear somebody say that cheaper PV has a rebound effect. It does, right? But nobody ever says that.
15%, something like that.
I don't know. I mean,
That's
but no one ever looks at the left-hand side of the Sankey diagram and says that reducing costs there has a rebound effect. They only look at the right-hand side. And I think I put it down to vested interests, actually. Right.
But overall, this idea that we would keep paying the same amount, roughly the same proportion. I mean, that does seem quite likely to continue to apply. It's just that we won't be paying for flows nearly as much. We'll be paying more for the infrastructure stuff. Yeah.
Right.
Yeah.
We'll be paying for the stocks of conversion equipment
Stocks,
as
yes.
opposed to the stocks of fossil fuels.
So the way
Yes.
in which that payment is phased is going to be really
Yeah.
important. Yeah.
Yeah, and I'm not sure that the rebound literature is very clear on which cost it is that it's often done from a user perspective. So it's assumed that electricity has a price, but of course, as we know, that price is partly due to the capital cost and partly due to the.
And to be fair to Julian, I don't think Eyre supposed that there was some constant rate of rebound. I mean,
No, we just observed that it was very high for steam engines in the UK during the Industrial Revolution, and it's probably very high for IT systems now. Yeah, we make more efficient IT systems, we are using more electricity in IT. Yes.
Martin, did you want to chime in?
Yeah, I just had a quick observation to that. If you remember when nuclear was coming on stream many years ago, the sort of the tagline was too cheap to meter.
Yeah.
And as we head towards sort of the PV systems where the marginal cost of energy is zero, you start to replicate what you see in the telecoms industry, which is instead of paying per phone call, you buy a package, and therefore the usage goes through the roof. And if you're paying for transmission capacity on electricity, and the marginal cost is zero, the drivers for energy efficiency, which I think we all agree is a good thing, disappears.
Yeah.
And
yeah, it's a really good point. And the way the market structures are designed has a massive impact.
Can I just say the long run marginal cost of extra electricity use is not zero actually, because you require more panels and more this and that.
Yeah.
But there's an important point, of course. Even now, even with fossil systems, a huge amount of the actual cost is in the distribution infrastructure.
Yeah. About
50%. It's not the way we price it in the market, but that's the reality.
And no industry does. I mean, you don't get charged a fixed cost and a variable cost when you buy something at Tesco's. You get charged a price for that item. Well, there's no other way of doing it.
I get buy one get one free actually.
I think Anne has a question online.
Yeah, Nick, thanks. I went back to the abstract in CRES to try and understand what you meant by the expanding sources, photovoltaics and wind produce work as electricity rather than via heat engines. And I don't understand that concept, that it's going to produce work rather than heat. Can you just explain that a little bit more, please?
Right, so there's basically what thermodynamics says is there's basically two sorts of energy. One is called heat, and I think people have an instinctive understanding of what heat is. It's things that I was going to say stuff that changes the temperature of things. That's not always strictly true, of course, but to a first order, it's true. Phase changes. Whereas work is anything else that requires energy. So we've got mechanical work, we've got electrical work, we've got magnetic work. There's all those different sorts of energy that are not heat are work, and that's what the whole discipline of thermodynamics is about, that distinction and how one's converted into the other.
I see. Okay. It's a different concept of work than what I'm used to hearing. Okay, that's fine. Thanks. Yeah.
It is, and the reason is that because its history was it was mainly done by human labour, so it made much more sense intuitively before the Industrial Revolution than it does now.
Yeah. Okay.
Yeah.
Thanks.
Nick, can I come back to your after diagram with two tallest pillars and again talk about the energy related products directly largely driven by carbon in the past. So now we haven't got carbon imperative. What is that tied to in terms of policy tools?
Well, carbon gets an increasingly weak lever as you move through the energy transition. I mean, you're not going to remove the last unit of carbon from the energy system by having a carbon tax, because you just think how big it would have to be. So,
but I'm turning it around and saying, how do you incentivise more efficient products now, because there isn't the carbon element benefit. So well, it's between the
point just made that you either do it through the price of energy, though that's actually quite a weak lever for something that only uses the amount of energy, say, of a laptop. It should be quite strong for heat pumps and even electric vehicles, but otherwise you do it through at the point of capital formation, essentially. You have standards for buildings, you have standards for vehicles, you have standards for equipment, and we know that works pretty well. I mean, a lot of the efficiency improvements we've seen throughout the world have been driven by standards more than by carbon pricing. Say it quietly in case the economists here, but
I'm trying to make that as a positive point, to say that actually you're already on the path for that. That will be the big that has the biggest chance to reduce the overall energy.
I mean, I think there is more work working in hand sense needed on what policies you need to drive the transition, but I can't see that product standards must be a big part of it, because we're talking about that's where the costs are.
Nick, your last element of carbon out of the system, the economist does have an answer for that actually. It's called direct carbon capture. What's the cost of that? $200 to $500 a ton.
Yeah,
that's where we ought to be pricing carbon right away. That I suspect is where we will then.
Ought to be, if all we cared about was the effectiveness of removing carbon in a perfect market, but that isn't what we care about, and the market is perfect. So
I think we've just hit past 12:30.
Okay, thank you, Nick.
Should we wrap up?
Yeah.
Yeah.
Thank you.
So